Hello, everyone. Welcome back. Today, we're going to be talking about things called Newman projections. So now that we're through the acid-base chemistry realm of things, we're moving on to what we're going to call the portion of the course that is all about um, structures and their 3D conformations. And so what we've been talking about throughout the course with a lot of our molecules is, when we look at something such as CH4, in the past, we've discussed how because this carbon right here is sp3, that means that it is tetrahedral, right? But the question becomes, what does tetrahedral actually mean? Well, what it means is that the angles between all of the hydrogens, right, the HCH angles, should be 109.5. But as drawn in this way here, it looks like it's a flat 90-degree angle, right? Now, the thing is, every molecule we're looking at is not flat. All right. Instead, it is actually in a 3D orientation that we haven't yet been exploring in the class. But we're going to start looking at things in terms of 3D space. And so what we're going to see is instead of looking like this structure that we've shown over here on the right, instead an actual molecule of CH4 is going to look a little bit more like this. So now what we've drawn is a 3D depiction of the molecule. And so these flat lines here are what we're going to call in plane, right? And they are essentially flat on the page, right? So those are as drawn. Essentially, if you were to look at them, it should look like that normally. However, these other ones that are on these wedges and dashes are a little different. So these wedges, the wedge is essentially showing that it is coming out of the paper towards you, right? So essentially, in real life, this would be closer to you than everything else because it's coming at you kind of slightly diagonally. And then this one right here, which is the dash, this one is doing the opposite. It's going back into the paper away from you. All right. And so essentially what these are going to be showing us throughout the rest of OChem is they're going to be showing us the 3D depictions of these molecules. And now with that being said, one thing I will say that's really useful for this lecture is this is when the model kits come into play, right? So model kits at this point are going to be very useful because essentially it's going to allow you to connect some of the stuff that I'm currently talking about with what you're seeing actually on the screen here. And so what we're going to be doing is we're going to be looking at these 3D depictions, and we're going to be drawing them in ways that allow us to show what we call conformers. So what we're going to do is we're going to look at ethane, right? A very simple molecule, right? It's a carbon connected to another carbon, and each one has three hydrogens. Now, in reality, rather than just being the flat things that we keep drawing, ethane is one of those that also has these 3D depictions, right? So each carbon, anytime you see something that's tetrahedral, it will always have one thing on a wedge, one thing on a dash, and two things in plane. So you can see that that is the case with this one as well. We have our thing on the wedge, our thing on the dash, and then our things in plane. And so these right here, this is essentially a structure of ethane, right? And we can start looking at this in a way that's going to allow us to see these conformers by looking at something called a Newman projection. And the best way that I can start by showing this is to label this as carbon 1, this as carbon 2, and then we're going to imagine looking down the bond in this direction, right? The question becomes, what will we see? Well, there's this picture that I've inserted here that's going to help us understand what we're looking at. So this is ethane, but drawn with a ball and stick model, right? So if you have your model kit, this is time that you'd want to recreate this carbon-carbon with a bunch of hydrogen sticking off of it. And you should get something that looks a little bit like this. And so what we're looking at here is this would be if we were actually looking towards that carbon, right? Where this one right here is what we would have listed as carbon 1. And then the one in the back we would have had listed as carbon 2. Okay? So if that's carbon 1, that's carbon 2. We also have all of our hydrogens sticking off of these. So I'm going to represent the bonds off of carbon 1, right? I'm going to give them a nice red color because that's going to help us in just a second. And then for carbon 2, the ones in the back are going to have this little blue color here. All right. So we're going to draw something that's called a Newman projection. And essentially what it's going to be is it's going to be as if we're looking directly down this carbon-carbon bond and we're looking straight at the center of carbon 1. All right. And so what this is actually going to look like as a demonstration for everyone, we're going to use a bunch of different colors to show this. Essentially, this red dot is carbon 1, right, as we have it currently depicted. In the back, we have carbon 2, right? We're going to represent it using a pretty big circle. And now what we're going to see is essentially carbon 1. If we look down at this picture again, we see that it has 3 bonds connected to it, right? We're going to represent those as well. And we can see that one of them is sort of pointed straight down, right? And the other two are kind of moving diagonally upward, right? So what we'll do is on to carbon 1, we'll point one straight down, and the other two will move diagonally upward. All right. And so this has sort of set the bond angles for carbon 1. On carbon 2, which is that big circle in the back, we see that it has one bond pointing about straight up, one pointing diagonally down, the other one pointing diagonally down the opposite direction. So for this one, what we do is we don't draw it from the center, right? Because we're just drawing the bonds attached to the carbon. So there's the one pointing up, and here are the two pointing down. So let me move my carbon 1 label so that everything is easier to see. So we've drawn out where all these bonds are, and now we have to show all of the hydrogens that are connected, right? So there's one hydrogen connected to each of these bonds. Because the bond between carbon 1 and carbon 2, we can't see it because we are looking directly at it. All right, so this right here is a Newman projection. It is a depiction of this molecule looking down that specific bond. And the thing is, right, it's very easy to tell when you're looking at this structure down here where everything sits, but we're also going to have to get an idea of looking at these bond line structures and using those to determine exactly what we're looking at. And so the thing is, though, the bond line structure depicts the exact same thing as the structure down here, right? Looking at the bond line structure, where our eye is looking down, right? This being our eye, it's looking down that bond. In plane, right down here is that first hydrogen. And that hydrogen to that eye should be pointing straight down, right? It's not going diagonal because it's flat, right? Since this line right here is flat, it is straight down. And then you can imagine to the eye, if this hydrogen is coming out of the page, right, whenever the eye is looking down that bond, it should essentially see that hydrogen to its right, right? Because it's coming out towards us. Therefore, if we're looking down that direction, it'll see the hydrogen to its right. And if we take a look at our Newman projection over here, that is the hydrogen that I will label right here in orange, right? It sees that hydrogen to the right. And then the one on the dash, you can imagine that's going back into the page. And so essentially, whenever the eye is looking at it, it should be to the left of the eye. And we see that that hydrogen is indeed to the left of the eye. And the same thing is true for the other hydrogens that we draw in on carbon 2, right? Since this one here is completely flat and it is above the bond where the eye is looking, it should be straight up. And then the other two, it's the same idea, where if one is coming out of the page, the eye looking at it, it'll see it on the right-hand side, and then it'll see the other one on the left-hand side. Okay? And so this right here is our Newman projection that's showing that 3D representation looking down that bond. And a couple things that we have to keep in mind here. One of them is that the angle between two groups oh, is called our dihedral angle. All right. And so looking at this Newman projection that we've drawn over here, all those hydrogens, right? You can imagine this is like an entire circle, so it's 360 degrees. That means the angle between any two of these hydrogens at the moment is 60 degrees, right? And if you add up all those 60 degrees, you'll get a 360 uh, angle. So that dihedral angle is going to be important for telling us some things a little later on when we start to talk about graphs. But at the moment, this is how we draw a Newman projection. Okay? But here's the thing. These bonds are not necessarily stationary. So if we look back at our ethane, right, and we draw it once again in the same manner as we did above, right, we're going to get a new Newman projection that'll help us describe this because it's going to be a little important for this next activity. Because the thing is, sigma bonds, right, so something like this guy right here in the middle, sigma bonds can rotate. All right. And it's not just rotation, it is a free rotation 360 degrees. All right. And this rotation is going to generate these things that we call conformers, right? And so this rotation would essentially be if we're going round and round the sigma bond, which is going to kind of twist where those groups are there. All right. So this generates these things that we call conformers. Okay. And so these are just rotations around a sigma bond, right? And there's always six conformers per bond. All right. So if you're looking at one sigma bond, it has six rotational conformers. We're actually going to look at all of them for ethane here. And we're going to start out with the conformer that we had already drawn. Right? If we look back at this Newman projection up here, we're just going to take this exact one because we're once again going to be looking down the C1, C2 bond. So once again, we have that hydrogen pointing downward, and we have all the others filling in where they need to be. And for this conformer idea, we're actually going to label these so that they're easy to track as we draw out these conformations, right? So this will be A, B, C, D, E, and F. So let's say we wanted to draw a conformer of this, right? A conformer is essentially going to be a 60-degree rotation around the bond. And anytime you're doing this 60-degree rotation, you're only going to rotate one carbon around. Okay, so we're going to try rotating the back carbon. So if we were to take the back carbon and start to rotate it, right, we're going to move all of the groups 60 degrees. So for example, HB would move 60 degrees, and 60 degrees away from HB is where HC is. HD will move 60 degrees, and HF will move 60 degrees. Notice how we're not moving any of the front hydrogens, right? They're all staying in place because we're not going to rotate that carbon. If we did that, it wouldn't be a conformer. We're just rotating the entire molecule. So once we've done this, right, the front carbon has not moved. Everything is exactly where it was before. HE, HC, and HA. But now HB has moved to where HC is. So they are completely overlapping at this point, right? And this is how we're going to draw that. We're going to draw them incredibly close, but keep in mind that they are actually perfectly overlapping. So HB moves to right there, HD moves to overlapping with HE, and HF overlaps with HA. All right. And so you'll notice that these two conformers are very different, right? Because in one case, everything is spread apart. In the other, these things are drawn close, but actually overlapping. right? And we actually have two different names for these types of conformers. When things are overlapping, we call this an eclipsed conformer, right? Because essentially one thing is eclipsing the other, just like solar eclipse when the moon goes in front of the sun, right? We have one atom in front of the other. The other one is what we call a gauche conformation. Now, for this one, I'm not entirely sure the reason that it's called gauche. I assume it's a chemist thing. Either way, so these gauche conformers and these eclipse conformers, essentially they're going to alternate when one comes and when the other one does, right? Because if we do another 60-degree rotation around this bond, right at this point, HB is now going to go 60 degrees, which will put it up there. HD is going to go 60 degrees. HF is going to move 60 degrees. And so we're going to end up in a situation where once again, the front carbon's hydrogens do not move, right? They stay exactly where they were, HA, HC, and HE. But the back carbon moves to where now HB is right there, HD is right there, and HF is right there, right? So we went from a gauche to an eclipsed, and now we're back to a gauche conformer. We can rotate this again, right? Because now we can continue moving things to where they haven't been moved before. Another 60-degree rotation is going to put us in a position where now we're back in an eclipse form, right? Front carbon, once again, never moves, but we end up where now HB is eclipsing with HE, HD eclipsing with HA, and HF eclipsing with HC, right? We do another 60-degree rotation, and we could see where HB is now going to move into this open area. HD is going to move into that open area, HF over there. So we have another form that looks like this. Perfect. Now we can do another 60-degree rotation. Again, this is why there are six conformers here, because every single one of these 60-degree rotations technically puts a different hydrogen into a different position, right? For example, HC and HD had never been eclipsing before, but they are in this example. HB and HA are now eclipsing, and then HF and HE are now eclipsing, right? So once again, we went from eclipsing to gauche to eclipsing. And now at this point, if we were to do another 60-degree rotation, we would actually end up with the original conformer that we had at the beginning, right? Because HB would go into this open space, HD into the top open space, and HF into the bottom right. So these would be the six conformers that we would see by doing these rotations, right? And essentially, if we were to put this in a very simple way, structures will constantly rotate, right? So conformations happen all the time. They are constantly changing. But one conformer is usually more stable than others. But looking at this, there's not necessarily a way for us to immediately know the stability, right? Where we're going to learn about the stability is through some energy tables, right? Because we have things called interaction energies, all right? And so these interaction energies are essentially energies that show how these things are interacting with one another, all right? So looking at these interaction energies, they are something that we call strain. All right, we're going to get into how to use them in a second, but first we have to understand what they are. Also, these A values for cyclohexanes, they'll be useful later. I just put the whole table in for now because we're going to reference it quite a bit. So they are things that we call strain. All right. And strain is essentially something that is denoting energy in terms of an excess of potential energy because something wants to essentially release energy to move away from strain. Okay. And there are two major types of strain. Okay. We have the first, which is steric strain. And steric strain is when atoms try to occupy the same space. All right. And the second type is what we call torsional strain, which is when electrons repel from being too close and it bends bonds. All right. And so when we look at these interaction energies, which we're going to talk about more in depth in just a second, essentially what you're going to see is that these gauche interaction energies are primarily due to steric strain, right? It is due to atoms trying to be in the same place. However, when you look at these eclipsing energies, usually these are due to still steric strain, but also, moreover, torsional strain. All right. So we're going to look at both of these strains. That way we have an idea of what they look like. And then we're going to come back to this and we're going to use some of these values to inform our confirmations. Okay. So first, let's look at sterics, right? You're going to hear the word steric, strain, or sterics a lot here in OChem. And the reason for that is because it's an explanation for a lot of things that we see causing instability, right? So for confirmations in specific, let's take a look at a structure that looks like this, right? And I'll draw all the CH3s so that's easier for us to see. Okay, let's say we wanted to look down this bond right here, right? Because the Newman projection is going to make it really easy for us to see some steric strain. So looking down this bond, right, the front carbon here, if we were to look at that, we would say that the CH3 that's on the normal line, right, so not the wedge or the dash, let's focus on the normal line first, is pointed straight down, right? Because from where the eye is, it is below it. And so it is pointed straight down because it's flat. That means that whenever we're drawing our structure, right, the way that I would think about these Newton projections is you have either a right side up Y or an upside down Y. And it's all defined by where that bond is that's flat. Right, this one's pointing straight down, so that must mean the other two are pointed up diagonally, so it looks like a right side up Y. So that would be our front carbon. Looking at the back carbon, right, we have above the eye in this case, the flat bond that's pointing straight up. And then that means that it would be like an upside down Y because the other two would have to go diagonally downward. So we already know that we have these CH3s on these sides, right? The top and the bottom. Whenever we're thinking about the wedge, since it's coming out towards us, that means that it's on the right side of the eye. So on the front carbon, it would see it here. On the back carbon, it's once again on the right. It would see it there. And then the other things that are on the wedges are the implied hydrogens, because remember this is still bond line, and so that does mean that there's a hydrogen attached, but since we already have one wedge, we got to have something on the dash. So that's where the hydrogens are. Whenever you look at this Newton projection, it looks just like the other one we drew, right? But we've abbreviated the CH3s. If we were to expand those, what we would see is essentially now, whenever we draw out these carbons, they each have three hydrogens hanging off of them. And what you'll find is it's pretty hard to draw these without having atoms in the same place. right? This is an example of steric strain, right? Because we can see down here, like these two hydrogens in particular, the way I've drawn them, it's very easy to see. And we denote the strain using these two crossed parentheses, sort of, right? So this right here, those are hydrogens bumping into one another. And wherever we see that, that is a sign of steric strain. Because remember, steric strain is when atoms try to occupy the same space, right? These two hydrogens want to be in the same space, but they can't. So they kind of have to fight over it, and that causes strain. And of course, the strain is an instability. So the more strain, the worse. Here's the thing though, when we look at sterics, what you'll notice is if we go back to thinking about that ethane that we had drawn beforehand, notice how these hydrogens don't really look too close to one another, right? Hydrogen is incredibly small, and all this space that's in between is just open. So because of that, we know that hydrogen is too small to cause steric strain, right? It's just too small. It doesn't actually have any interactions in this conformation. Now, whenever we look at this, right, let's look at the gauche side of things, because once again, this is all about sterics. Notice how there's nothing here with just a hydrogen, right? Everything over here, it's all groups bigger than hydrogen, right? Everything there is like CH3 interacting with CH3, CH3 interacting with Br, so on and so forth. But there's nothing there that shows H interacting with anything. They never do in terms of these gauche interactions. All right, if we look at our second type, which is torsional strain, the first thing that you need to know about torsional strain is that, of course, it does occur in these eclipse structures, right? So let's take that ethane example, but let's look at one of those eclipsed forms. So earlier we drew some eclipsed forms that looked kind of like this, right? And what we see is that, first of all, the hydrogens are now a lot closer than they were. But the thing is, they're still not really putting much steric strain on the system because they're still small. But if we take a look at what the bond actually looks like, right, we're going to draw a little orbital picture because once again, everyone likes orbital pictures. Right, looking at this, we're only going to show one bond to the hydrogens. They're sitting right here, but the thing is, each of these bonds have electrons in it, right? And we know that since electrons are negatively charged, if you have a couple of them that are close to one another, they are going to repel, right? Because negative repels negative. So what this is actually doing is these electrons are pushing away from one another, right? And what that's doing is if you've ever tried to push away two things like that on a bond, you can imagine it like the bond between the two carbons. This is like when you bend a pencil, right? It's like you're pushing on both ends, and the center of the pencil is now feeling that strain, right? So it's putting strain on that bond. And the thing is, that strain is much more than the steric strain, right? Because essentially the electrons want to push away as hard as possible. Sometimes atoms can kind of move a little bit to get out of the way. So that being said, one thing that is true is that torsional strain is always higher in energy, right? Or we can just say worse for stability than steric strain, right? So it's always worse, which tells us that eclipsed strain is also more than gauche strain. All right? Because essentially in the eclipse form, right, that's why we have it up here listed as these eclipse interaction energies with torsional strain, is much more than those gauche interactions with steric strain. And so what that means for us is when we look at two different Newman projections of the same molecule, just different conformers, what we'll find is we can pretty quickly tell which one is going to be more stable than the other, right? Because if we look at both these structures, it's pretty obvious because hydrogen doesn't have any steric strain, it just has torsional strain, right? That's another thing to keep in mind because look up here, you'll see that hydrogen appears quite a bit in our actual eclipsing strain energies table, whereas it didn't in our gauche table. So we would say this structure on the left is more stable because it has less strain than the structure on the right, which has high torsional strain and is therefore unstable. And as a matter of fact, we can actually look at this in terms of energy, and we can look at it in terms of dihedral angle. All right. So we can make this graph, which is dihedral angle on the x-axis, energy on the y, and let's take a look at our dihedral angle between two hydrogens that we choose to look at on our uh, conformations, right? Let's go back up and look at these ethane conformations. Let's say we were looking at HC and HB, right? And we're looking at the dihedral angle between them. Right here in this structure that I have circled, or I guess boxed, right? HB and HC are overlapping. So we would say this has a 0-degree dihedral angle. If we look over here on the next structure, right, HB and HC now have a 60-degree dihedral angle because they're 60 degrees apart. Next up, HC and HB, now they are 120 degrees apart, right? Because remember, each rotation we're adding 60. And then over here, HC and HB are now 180 degrees apart. All right. Now, looking at these, at 0, it's an eclipsed conformer. Therefore, it's going to have high energy. At 60, it's gauche. At 120, it's eclipsed. At 180, it is gauche. So if we think about that in terms of energy, right, at 0, this was an eclipsed conformer. So it's going to be high in energy. But then at 60, as we saw, this was a gauche conformer, so it's going to be low. At 120, it's another eclipsed conformer, right? So it is also going to be high in energy. And then at 180, it is another gauche. So it is going to be lower in energy. So essentially, as we turn that carbon in the back and we change the dihedral angle, our energy is going to kind of do this little wave, right? It's going to go up and down and up and down, and it's going to keep doing that as we rotate. All right? So, needless to say, eclipsed interactions are much higher in energy than gauche interactions. All right? Now let's start thinking about this in terms of actually calculating energy. Okay, and how we're going to do that is we're going to once again look at a Newman projection, right? But what we're going to do is we're going to look at one that is going to be a little more interesting. So let's take a look at butane, right? I'll draw it out a little nicer for us here. So let's say we were looking down this bond of butane. Okay, we can fill in so that we know where everything is, right? On the wedge should be a hydrogen, on the dash should be a hydrogen. Same thing over here, on a wedge should be a hydrogen, on a dash is also a hydrogen. So, if we wanted to draw a Newman projection of this, what we would do is the first thing we would want to do is we want to draw out our circle, right? It's a good way to start. And we can say that the first thing that's on our Newman projection is this methyl group, right? And it's pointed straight down because it's on the flat thing. So it should go straight down there. And then the others should go diagonally to either side. And that's where that methyl goes. On the back carbon, above where the I is, so pointing straight up, is the methyl there, right? And then we know that everything else here is just hydrogens, so it's not that important at the moment. So looking at this structure right here, we have to determine what the energy is, right? The energy of this should actually be zero, because whenever we look at it, there's no steric strain, because even though there's these methyls, right, they're adjacent to hydrogens, and hydrogens never have steric strain. There's also no torsional strain. Therefore, this structure is sitting at an energy value of 0 kilocalories per mole. All right? All of our energies are going to be measured in kilocalories per mole because if we look back at that table, you'll notice that every energy value is listed as kcals per mole. So if that's 0 kilocalories per mole, let's see what happens if we do a 60-degree rotation, right? What we'll do is we'll take the things in the back. So that's going to be our CH3, this H here, and this H here. And we're going to rotate them that 60 degrees. And that's going to take us to an eclipsing conformation, right? So in the case of the eclipsing conformation, the first thing we got to do is remember that front carbon does not change. The back carbon does, though. And now we have these things that are completely overlapped. So if you were to go back and look at that table, by the way, it is on Canvas. Make sure that you get a downloaded copy of it. You would see that our hydrogen and CH3 eclipsing interaction, that is going to have a value of 1.4 kcals per mole. All right. And there are two of these, right? Because we have the hydrogen CH3 overlap there. We have the hydrogen CH3 overlap here. So that's going to be an additional 1.4 kcals per mole. The next thing is we have these two hydrogens overlapping. So if you look at the hydrogen-hydrogen eclipsed interaction, that's going to come out to a value of 0.9 kilocalories per mole. So if we're looking at our total energy, right, we can label it as ETOT, which is just total, E total. We would see that that should come out to 3.7 kilocalories per mole. Right, so the difference in energy, because remember that the total energy for the conformer over here is zero, the difference in energy between these two is 3.7 kilocalories per mole. Right, but there are other conformers that we can draw, because remember there's 6 of them in total. So if we do another 60-degree rotation, right, what we'll end up with is now we have come back to a gauche form, and we've moved everything clockwise. So now we have a hydrogen right there, a hydrogen right there, and that other methyl group has come into that position. Now we see something that actually matters in this orientation because these two methyls should have interactions because they are large, right? They're going to have steric interactions. And if you look at our little table, the CH3 CH3 gauche interaction shows up as 0.9 kcals per mole, right? But once again, these don't interact with any hydrogens, right? Hydrogens are too small and they never have steric interactions with these carbons. And so what that means is that our total energy for this conformer is 0.9 kcals per mole. All right, so you'll notice that looking at this so far, we see that we have different energies for each and every conformer, right? And the same thing's going to be true if we do another 60-degree rotation, right? If we rotate this once again, we're going to end up in a position where now we actually have both methyl groups, both those CH3s overlapping. Okay. So if we wanted to do the interactions for this here, right, we know that we have everything overlapping, so everything's going to have a value. We already talked about the hydrogen-hydrogen eclipsed interaction, right? That comes out to zero point 0.9 kilocalories per mole. And the thing is, we have two of those, so we should have another zero point 0.9 kilocalorie per mole. But then our methyl-methyl eclipsed, this is going to have an even higher value, right? Because the bigger the group, the more steric strain it comes with on top of the torsional strain that we see on the bond. So in this case, the CH3CH3 eclipse, if you go back up to the table, whoops, it's 2.6 kilocalories per mole. So our total energy in this case is even higher. It sits at 4.4 kilocalories per mole, right? So we had one that was at 0, one at 3.7, one at zero point 0.9, and one at 4.4. So you'll start to notice that each of these conformers can actually be very different energies depending on what is attached and what interactions we see. So we're going to do another rotation because remember we have 6 of these that we have to look at. So we do have to talk about each of them. And this one, we've now moved everything on the back carbon clockwise once again. And we see the only interaction here is the sterics between the two CH3s. And so once again, when we look at our CH3, CH3 gauche, that comes out to be zero point 0.9 kilocalories per mole, right? So the total energy of this conformer is once again 0 0.9 kcals per mole. One more rotation will get us to our last conformer before it'll reset and everything will be back to its original positions. And for this one, it's going to be another eclipsed form. But for this one, it's actually the exact same numbers as the one up here in the middle, right? We have two hydrogen CH3 eclipsed and one HH eclipsed. So I am not actually going to show the math for that one due to brevity. It is once again 3.7 kilocalories per mole, right? Because another rotation of 60 degrees is going to take us back to the 0 kcal per mole conformer. So when we think of these conformations, right, we can say, first of all, that this conformer over here is our lowest energy conformer, right? It is sitting at 0 kcals per mole. That's as low as you can physically go. On the other hand, this one down here that I'm now circling in green, this is our highest energy conformer. Okay? What this is telling us is that for the most part, the structure is going to sit in the orientation that is the lowest energy conformer, but it can rotate, right? And the rotation is going to pass through each and every single one of these conformers until it returns back to the lowest energy state. And with that being said, the overall bond rotation energy is very simple, right? The energy is equal to the Ito of the highest minus the total energy of the lowest, right? So if we were to look for the energy of rotation here, it would be 4.4 minus 0, which would be equal to 4.4 kilocalories per mole. So essentially, to get this bond to fully rotate around, it's going to take 4.4 kilocalories of energy. All right? This is just a little important fact that you will not be tested on. All right. That being said, that is unless I provide it as a bonus point option. Okay, something to keep in mind. Now, let's actually graph this energy, right? Because we're gonna take a look at something that's actually a really interesting, um, I guess, outcome of this. Let's graph our energy in terms of the dihedral angle between the two methyl groups. All right. So, looking at this, we are going to have a little graph here. It's going to start at 0, right, where they're both completely overlapped. And then we'll do every 60 degrees, right? So we'd have 180 here, 240, 300, right? Because 360 would be a full rotation. We don't have to show that. And this y-axis is, of course, our energy in kilocalories per mole. So let's take a look back up here. Our lowest energy conformer, you'll notice, is where the carbons, those CH3s, are 180 degrees apart. All right, so we're going to draw that over here where our 180 is. That's our value of 0. All right, now then, if we look at the rotation from this, right, one rotation is going to put us in a position where we're essentially looking at the carbons being 120 degrees away from one another. So at 120 degrees, it's at 3.7 kilocalories per mole, right? So we can put that value up here, and we're just going to go through and we're going to fill in everything else. The next one would be if they're 60 degrees apart, which would be this third structure over here on the top right, right? So 60 degrees apart, they're sitting at zero point 0.9 kilocalories per mole. So this would be our zero point 0.9. At 0 degrees, though, that's where they're completely overlapping, right? And that was our highest energy conformer. So it sits up here at 4.4 kilocalories per mole. The other two are our other two conformers that end up being rotated between 240 is also at 3.7 based on what we have, and then 300 is back at zero point 0.9. So looking at this energy landscape, it's a little different from the other one we saw, right? Because the other one was just up and down. This one has some things that are kind of in the middle. But what you'll notice is there's a very interesting relationship that we can see just based on the angle, right? Our highest energy, which was the 4.4 right here, also happens to overlap with a complete overlap of the two methyl groups, right? So 0 degrees is complete overlap. And then if we take a look at where our lowest energy was, right, that would be this one here. This conformer happens to be the 180 degrees, which is completely opposite of one another. And these actually have names. All right, so if we take a look at this um, Newman projection, where the carbons are 180 degrees apart, right? This here is what we call the anti-conformer. And what this means is just that the two biggest groups, right, in terms of size and sterics that they would uh, cause. So something like a hydrogen is super small, something like a methyl is really big. The more things you attach to that methyl group, like more carbons, are going to make it even bigger. So it's where the two biggest groups are 180 degrees apart, and it is usually the most stable conformer. This contrasts to the other conformer that we were talking about, which was the one where that dihedral angle was at 0 degrees, right? Because those two CH3s were overlapping. right? We call this conformer, where we have no dihedral angle. This is the totally eclipsed conformer, right? Where the two biggest groups are eclipsed, and this is usually the least stable conformer. All right. So essentially, as you rotate through these, you're going to get this sort of energy diagram here where it's going to have to go up and down these hills in order to get that rotation done. But the most important conformers are always your highest energy, right, which is the least stable, and your lowest energy, which is your most stable, and those are called either anti or totally eclipsed based on which one you're talking about. Now, with that being said, this is about everything that you need to know about what Newman projections are showing us. That being said, in the next lecture, we're going to go through some problems and we're going to talk about drawing more complex Newman projections because for this lecture, we were really just focusing on what this chart means in terms of everything here. So next time, we're going to get into the meat and bones of talking more about these different ways to draw Newton projections, as well as we're going to start looking at a couple cycloalkanes. And then after that, we're going to talk about cyclohexanes, their importance, and what it looks like whenever we're actually working with those. So that being said, I'll see you next time to talk about those Newmans.